Go. Yesterday was unit circle. Today is sum and difference and double angle with triangle. So these are right triangles. Here's the first thing. It's how you draw your triangle. And here are your steps. Some of you really like steps. I really like steps. I like having a definitive process that works for every problem, and this does. Determine the quadrant and draw the triangle in it. That is going to be your first step. So all of these triangles are going to look like this. Depending on what quadrant they're in, you're going to always have a 90-degree angle. They're always right triangles, and that 90-degree angle is going to be with the x-axis, no matter where you are. So for example, if you had a third quadrant triangle happening, it looks like this. So think about kind of bow tie, like unit circle style. Out to the and down. Out and up. Interpretive angles for the day. There you go. After that, you're going to need to find a missing side length. But what you're going to be given is like a SOHCAHTOA style sign of theta is 1/3. And you're going to put 1/3 at the right spots, opposite and hypotenuse. Then you have to find the missing angle, or sorry, the missing side. And then determine which formula you're going to use. And use the triangle values to replace sine or cosine or tangent. Just like yesterday when we had like cosine of pi over 4, and then we made that radical 2 over 2. Here you're going to have sine of a, and we're going to put in 1/3. It's going to replace the whole thing. And then simplify and rationalize. So the first step is figuring out where your quadrant is, and you do that based on this description here. So this takes a little bit of practice because sometimes these are kind of funky. If we have a triangle that's between pi over 2 and pi, what quadrant is that? 2, absolutely. And if you have like if you're like, whoa, how did that just happen? Like it's this diagram, and it's just the quadrantal that you're looking at. 3 pi over 2. So this guy, if we're between pi over 2 and pi, then we're over here. What if we're between pi and 3 pi over 2? What quadrant are we in? Yeah, quadrant 3, we're down there. What if we're between negative pi over 2 and 0? Here's where it gets a little tricky. So negative pi over 2 is up here, but remember negative angles go this way, right? The opposite direction. So 3 pi over 2 is the same as negative pi over 2. So that is quadrant 4. This is the same as 3 pi over 2. And this last one's really tricky. I would not do this to you on a regular basis or on the test. If we were going to do negative 3 pi over 2 to negative pi, so if I start here and go negative 3 pi over 2, I'm going this way, 1, 2, 3 pi over 2. And if I start here and go negative pi, I'm going here. So that's actually quadrant 2. You might see something like that on Math Excel. You can always ask if you need help placing those quadrants and how to get help with them. All right, here we go. Now we're going to do a problem like from start to finish. It says for 5 and 6, find the value of the following functions if x and y are between 0 and 2 pi. So we're in quadrant 1 for both of these, which is nice. Try to be gentle as we start a new concept. So we're in quadrant 1. And we're finding sine of x plus y. So what I like to do to start is write out what I need. So I'm going to do that over here because we're going to do some other math over here. Sine of x plus y from our formula sheet, and you can grab one if you want, is sine of x cosine of y plus cosine of x sine of y. And in this part of the unit, we're going to replace cosine of x and cosine of y and sine of x and sine of y. We're going to replace that whole thing with a triangle value. So this is going to be replaced by a fraction. So is this. So is this. And so is this. You just need to figure out what those values are for the triangles that we're given. So now let's set up those triangles. Our first triangle is this guy. Sine of x equals 3 over 5. So sine is opposite over hypotenuse. And the reason I love doing this unit like after break is because this gets us back into right triangle trig, which shows up on the ACT quite a bit. So I mean, you know, the ACT is all over the place, but you will see some right triangle trig on. So here, sine is opposite over hypotenuse. We're in quadrant 1. So here's my triangle. Opposite is 3. Hypotenuse is 5. Do you know this special right triangle? What's the missing side?
4.
Yeah, it's 4. It's a 3, 4, 5 right triangle. Those special right triangles are really helpful. I use 3, 4, 5 a lot in this unit. Because I used to not allow calculators in this unit, and then like 3, 4, 5, I use it on like every problem, which is nice and small. If you don't know, if 3, 4, 5 right triangle is just not something that you want to spend brain space on, how would you find 4? Well, you would do this. 3 squared plus b squared equals 5 squared. And since you have your calculator for this unit, you can do this. B squared equals, subtract that 3 squared over. Put that in your calculator, take the square root. That's how you can do it in one step. Pythagorean theorem in one step. And I use a lot of special right triangles, and some of them are probably triangles. Like 3, 4, 5, but the next one is also a special right triangle. You probably don't have that one memorized, and that's fine. Because Pythagorean theorem, you can always do. Okay, so let's fill in what we have. So from this triangle, and here's the angle that we're referring to. We had sine of x, this is our x triangle, is 3 over 5. And we needed that right here. We can also get cosine from this triangle. What is cosine of x? Cosine is adjacent over hypotenuse, so it's 4 over 5. Cosine of x is right here, 4 over 5. And now we're going to do something similar for triangle y. So here we have 2 different triangles, 2 different angles that we're using, and we're doing the sum formula with them. So here we go to triangle y. Triangle y comes from this guy right here. Again, I'm given sine, so this is opposite, and here's my hypotenuse. Opposite out here. Hypotenuse is always going to be like that unit circle. This one I don't have memorized, so let's do the math. 12 squared plus b squared equals 37 squared. And then you're just going to subtract over that 12 squared. And take the square root, or whatever order you like to do that in. If there's another order that you like for Pythagorean theorem, like if it's really satisfying to you to write out like a squared plus b squared equals c squared and square everything and subtract over the 144, I will not take that away from you. I like the Pythagorean theorem as well. You are welcome to write out every step, or really none of the steps, because you can do it all on your calculator. You should get 35. Did you get 35? Okay. So from this triangle, we need the sine of y and the cosine of y. Sine of y we were given is opposite over hypotenuse. Cosine of y is why we needed to do the Pythagorean theorem, is adjacent over hypotenuse. So cosine of y, 35 or 37. Sine of y was 12 over 37. I'm going to put my symbols in here. Here we're adding, here we're multiplying, and now you probably see why I give you a calculator for this unit. Honestly, it's really hard for me to design problems that are small enough, like where the numbers stay small enough for the whole entire problem to not have a calculator. So it's harder for me, really, than it was for students. So, you always get a common denominator with these, which I think is lovely. It's kind of one of my checks. So like, before I add, I should have a common denominator. 3 times 35 is 105. 5 times 37 is 185. 4 times 12 is 48. 5 times 37 is 185. In that common denominator situation, I have messed something up if I don't have a common denominator. And that goes for these as well as if we were doing cosine of x minus y as well. And then 105 plus 48 is 153. And that is your final answer. It is ugly, and there is no way to check it. It's not like when we had unit circle problems, and at the end, we could put our original problem into our calculator and our answer in and make sure they were the same decimal. There's no real way to check your work on these, which I don't like, because I'm the one who gets to stand up here in jazz hands and like I don't like I like to be able to double check and triple check my work. So. I like the unit circle and stuff better, but the triangles are such a great thing to just work with and work with. Okay, let's do tangent of x plus y. Again, with this one, we're in the first quadrant as well. I gave you cosecant on purpose. We don't like working with cosecant. What would we rather work with? What can we work with instead easily? Sine of x, yeah, absolutely. So if cosecant is 5 over 3, I don't do anything else first. I flip it and write 5. That's a really nice first step. The other thing I'm going to do before we do anything else is write out tangent of x plus y. Tangent of x plus y is tangent of x plus tangent of y over 1 minus tangent of x times tangent of y. So once we get our triangles drawn, we need tangent for both triangles. And tangent is, if we're thinking SOHCAHTOA, tangent is opposite over adjacent, right? That's where you're going to go on. All right, let's do our first triangle. So we're going to make a triangle for x, and we're going to make a triangle for y. We've already started our triangle for x by just flipping that there for 3/5. So sine is 3/5. So that's opposite over hypotenuse. Oh, hey, what's our adjacent leg? 4. Okay, so if we want tangent here, tangent of x, tangent is adjacent, opposite over adjacent. So it's 3 over 4. All right, let's do our y triangle. For y, we're given cosine. Cosine is adjacent over hypotenuse. This may also be a triangle that comes back to, yep. If not, again, that's okay. So adjacent is always going to be on your x-axis here, your adjacent leg. So that's 5. Your hypotenuse is 13. Does anyone remember this special right triangle? Yeah, it's 12. Again, you are welcome to do Pythagorean theorem. And solve for b. It's okay if you don't have... I use 5, 12, 13 a lot too. Because like when it comes down to it, sometimes I'm just making tests and making up problems and just use triangles that are fresh in my brain, and those are the easy ones, to be real honest with you. So this is just the background work. This isn't, this isn't the pre-calculus part. All right, so tangent of, not x, tangent of y is opposite over adjacent, so 12 over 5. And now you put those into your equation, plug those into your formula, and math. So this one and this one. Again, I'm not going to put it in as tangent of 12 over 5. That's not what's happening here. Tangent of y is 12 over 5. The whole tangent of y goes away. The whole tangent of x goes away. It is rough if you, like, there's no coming back from that mistake, so don't do it. I have a ton of middle steps on this. And you are going to have some problems where you have to do the middle steps by hand because there are radicals happening. On this problem, you can put it into your calculator. You don't have to do any of the work by hand, which is really nice. So however you choose to do it, I mean, I found a common denominator on top, and I see some of you doing that. Like finding a common denominator. So that's going to be 15 plus 48 over 20. That's the numerator. So you're going to get 63 over 20. And in the denominator, you're going to do that 1 minus. But your calculator can do this without those 5s and 4s very easily for you. And honestly, I encourage you to use your calculator to its fullest extent. Do you guys want me to give you a second to get that in your calculator and try it? Okay. Let's finish up with this one, because it's going to have some radicals in it. And then I think we'll do like cosine, sine, and tangent of 2 beta tomorrow. Those are pretty easy. Or maybe we'll do maybe we'll do those on Friday. Okay, so if we're doing cosine of a minus b, here's what we need. Again, I like to see that equation in front of me and know exactly what I'm plugging into. So I'm going to do cosine of a minus b is cosine of a cosine of b plus sine of a sine of b. And that's 2 triangles. You get all the values for our a's from one triangle and all the values of b's from the other triangle. So our a triangle is given, the information is given to us from this right here, and this. So if I'm going negative pi over 2 to 0, what quadrant am I in? 4. Yeah, quadrant 4. So just like we did when we were in quadrant 1, your triangle should come down and then have that right angle on the x-axis. It's really important that you're on the right spot there. And then cosine is adjacent over hypotenuse. So adjacent is always going to be on your x-axis there. Hypotenuse is always like what was 1 on the unit circle. And we're going to have to do a little solving here. So, let's see, 2 squared plus b squared is 3 squared. I am going to do Pythagorean theorem here. So all of this gets just a tiny bit more tricky when we start introducing radicals and having to do operations with radicals. But like you saw yesterday, that's a really important part of working with the unit circle and I think working with trig in general. Okay, so this is our A triangle. So all our values for A's come from here. So cosine of A was 2/3, and I saw some of you already go ahead and put that into your equation, which was great. Sine of A, sine is opposite over hypotenuse, so sine of A is radical 5/3. And now we need to do our B triangle. Here's our B triangle details. B triangle is in quadrant 1. Again, we're given cosine, so that 4 is going to go along the x-axis, 7 is the hypotenuse. And we're going to end up with some radicals on this one as well. So 4 squared plus b squared, 7 squared. At least the numbers aren't ridiculous on this one. Always put it into my picture because I refer back to that picture to get my values. So again, I'm replacing the whole thing. Cosine of B is the same as 4/7. Sine of B is opposite over hypotenuse, so square root of 33/7. And now we have fractions and radicals to deal with. So on our first fraction, we can just multiply here. This is nice. 2 times 4 is 8. 3 times 7 is 21. Common denominator here, 3 times 7 is 21. That's always going to happen whether you're doing sine or cosine. And then the last thing, we have to do 5 times 33. Remember, with radicals, we talked a little bit about our radicals yesterday. With our radicals, we can multiply those as long as they are the same kind. So they're both square roots. Help me out. What is 5 times 33? 165. And then these have a common denominator. We want to break down 165 if we can, but 165 was 5 and 33. 33 is 3 and 11. I don't see any perfect squares. So that is your final answer. And we'll do double angle on Friday before we do mixed practice because the scavenger event tomorrow is all from the
Yes, Jay.